Okay, so good morning everyone. Yeah, so yesterday I was talking about some of the brief overview of our center. So we are a subordinate office under the Ministry of Earth Sciences. So our job mainly is to provide the numerical weather prediction forecast, as well as our major mandate is to provide them all the institutes which are coming under Ministry of Earth Science. So any model they have to run, like it is an ocean model, ocean forecast, which is very important for fisheries, or like for example weather for IMD. So anybody, those who want any model they have to run in their own institute of our MoES sister organizations, they need initial conditions as we discussed yesterday. So observations, so as the NWP is an initial value problem, we need initial conditions to forecast any parameter. So what our center will do is it will create we receive all the global observations, like it is from the ships, from the satellites, from the aircraft. So all the observations globally we receive, including all the aircrafts that are flying around the world. That all the data we receive. So we assimilate in our center and we create a best state of the atmosphere. So best state means in the current state, what is the temperature profile, what is the humidity profile, what is a whatever the parameters that are important to run a numerical weather prediction model. So all those parameters we give them the initial conditions and we supply all our sister organizations. That's what we actually do. Apart from that, we are also running several numerical weather prediction models and also the climate prediction models. So that is what I am going to discuss. So basically I am going to give you an overview with more in-depth analysis compared to yesterday's talk. So yeah, next. So just I already discussed with you, there are various centers under the Ministry of Earth Sciences, those who don't know. So there are 1 to 5 I listed. 1 to 5 are basically atmospheric sciences and seismology sector. So those who are working on the seismology, we have another center called National Center for Seismology. So all the 1 to 5 are related to the atmospheric, weather and climate and ocean, including ocean. Okay. So there are NCMRWF, IMD and IITM Pune, and there is an NCMRWF. So all these centers, NIOT, Chennai, which is so they develop like deep ocean ships and all those things. Further, that NIOT will develop. Okay, so those 1 to 5 are like atmospheric and sciences and seismology sector, and 6 to 10 is ocean science and technology sector. So those who are interested in the ocean science engineering and all those things, they can look into these 6 to 10. That those are centers for ocean science and technology sectors. So what our center will do? So we develop continuously advanced numerical weather prediction systems with increasing reliability and accuracy over India and also neighboring regions. So what our center will do, not only India, we actually yesterday I showed you that we are running global systems, global weather prediction models. Apart from that, we are also supply, particularly there is a BIMSTEX, I don't know how many of you heard. So I think recently PM Modi also invested and gave millions of dollars to that BIMSTEC center for BIMSTEC organization. So BIMSTEC is like, all the countries that are on the edge of the Bay of Bengal. So like Bangladesh, Nepal and all those countries. So for that, our center is actually a BIMSTEC center for weather and climate. Okay, so all the whatever the charts, whatever the services we offer, we also offer to all these Sri Lanka, Bangladesh, Nepal, and Myanmar and Thailand, all those countries adjoining to the Bay of Bengal. Okay, so that is a BIMSTEC center for weather and climate. So that is another center which is situated in NCMRWF. Okay, so this is one thing. So not only for India, and also the neighboring regions that we do, and another thing is to demonstrate new novel applications using NWP outputs. So every day we generate a lot of forecast. We supply to defense sectors, Navy, or Army, and all those things. Apart from that, we also send our forecast to renewable energy sectors and several private companies. Like we have 30-40 private companies under the renewable energy sector. We are supplying our data to them so that they can actually see how much solar input they can get, solar forecasting or wind energy forecasting. So all those institutes, they take our data and on a real-time basis. Okay, so that also we are supplying recently. Not recently, we are supplying I think from past 10-15 years. Okay, so next. Okay, so
there was a publicly available website. Call specific sending to some organization.
Yeah, so if you ask me, so not all the data we send on real-time basis, because real-time is most important. So unless we have MOU, we don't send real-time data. Like for example, today, next hour, 5 hours, I want a forecast for next 10 days from today onwards. So that real-time basis we don't send. But from the historical, like if you want to work some research purpose or without any, not involve any business. I mean, okay, like that. So if it is involves any money related things, so you have to take a MOU with us, and we will only supply the data with.
So we can ask the questions at the end. Huh?
So that we will on real time basis we
just
don't.
Note down your questions. We can ask at the end.
So yeah, so just to know, I mean, I don't know how many of you are from weather science and all of things. So I just kept why we forecast weather. So I don't. Anybody already that weather affects nearly everybody. Okay, so I mean it saves life, reduces property, all those things are general things we know. And the thing is, we won't give an exact forecast, but at least we have some anticipation. If I go today, what is could be the weather in the evening? That type of plans actually you can do. Even my wife also at home, she asked me whether I can do some sort of clothing today. So see, it went like deep inside in every home also. So shall I take my umbrella? My daughter asked, shall I take umbrella today or not in the rainy season? So such type of things, I don't know how many houses they will ask you, but in our home they ask me sometimes. Okay, sometimes it may good, sometimes it may bad forecast. So it happens both ways. So but at least what we can do, we can anticipate something. Okay, there is a cloudy weather. We can't tell 100% sure, but we can tell that okay, there will be some cloudy or some cyclone happened in next few days. That type of forecast now, I mean the NWP models are pretty good there forecasting. So yeah, that's what I told. Forecasts are often utilized to take many important decisions on a daily basis. Yeah, so some major important things I listed here. One is a monsoon. So monsoon, it actually has a good percentage in the country's GDP. So I think there are sometimes it affects 2.5% of GDP in the whole country. So that type of situations we got due to the monsoon failure. So it is most important in terms of government plans also. I mean, suppose they want to plan what would be this monsoon season rainfall, so that it affects all the agriculture people and all those things. So government can send them some information that okay, this season will be dry or this season will be wet. So that type of information, it is very much crucial for the government also to plan for next 4 months or 5 months. So that's why it is most important in terms of monsoon perspective, and also cyclones. Already Orissa is most affected for the cyclones. So cyclone information. So I think 5 days before, we at least came to know how much the cyclone can affect in which coast with some probability. So that type of situation we are now. At least yesterday, I think Professor Mohanty also mentioned that at least next 48 hours, 50-kilometer range, at least we can tell that where the cyclone hit the coast. So that type of capability we have now. And another important thing is a fog prediction, because maybe here I don't know, but at least in Delhi, in all those places that is most affected by the fog. So it actually affects millions of dollars in every year. I mean, in Delhi itself, sometimes due to the fog, they'll transfer all the flights to some other airports. So that's such type of situations we have. So I mean, so everything is related to the money. I mean, in millions of dollars, if we don't give proper forecast, it affects all these private and public programs. So it is most important. Another one is, I know already this, you are hearing a lot, air quality especially. So that also we offer. At our center, we are also integrated the chemical models in our NWP systems. NWP also has a chemistry model, so that will give the air quality information as well. Okay, not only the dynamics or cyclone or related, but also gives the air quality related parameters. Particularly the PM 2.5, whatever you are taking in this area. All those information we actually give for in the Delhi region, which is most affected in the winter periods. So yeah, like that you have a flood, avalanche information. So avalanche means, see, our model is a global model. It has also a component. Yesterday, I don't know how many of you noticed. So I put in my first slide the sea ice model. So we have a sea ice model. Not only land surface, atmospheric and ocean model, we have another sea ice model integrated over total coupled modeling framework. So we have a sea ice model. So what it will give? It will also give the information of the sea ice forecast. Okay, why it needs to us? So because government of India has also invested some money in the Antarctic and Arctic places. So we also need that information that when the ships can move and other things. So that's why we also give the information of CIs and that snowfall and all those information we provide to them. Okay, so I think I already mentioned the wind energy and solar energy, which is the most important. Private agencies are taking major part in this. So we are actually from last year onwards, we are actually sharing them with some money also, because government has gave a mandate. We are selling our forecast to those companies that are in that which involves the money related stuff. If you want to do research, you don't, we can give free. But if it is involves some money or anything, so then we will offer them with some money. Okay. Yeah. Yes. Yeah. So yeah, I just kept here what type of ranges of forecasting we have. So we have a very short range, which is called nowcasting. We call it is the next 2 hours. So I think when you go to your home or next 1 hour, what will be the condition like thunderstorms? Especially I think Odisha is most affected by the thunderstorms in the pre-monsoon. So it is basically important for those nowcasting things. And there is a very short range forecasting up to 12 hours we call. Short range forecasting is like 12 hours to 72 hours. Any forecast we give from beyond until 72 hours is called a short range forecasting. Okay. Suppose if we offer a forecast next 10 days, that is called a medium range forecasting. So basically our center is a national center for medium range. So medium range is our major goal is to provide 10-day forecast. Okay. So extended, there is also another called extended range. So beyond 10 days. Suppose I want some information about next 1 month. Okay. Like multi-week forecasting. Okay. What is the situation of weather this week, next 2nd week, 3rd week, and 4th week? So this is most important for a drought and other places. Why these are important is because there are some slow phenomena and there are very fast phenomena. Like fast phenomena means like I told you that thunderstorms. It is very fast, fastly it will grow and dissipate. So there are very short phenomena. So that type of short phenomena they have nowcasting is most important. But the slow phenomena is, suppose let us say drought is a slow phenomena. So even though so it will evolve, it will increase slowly. You don't see the effect of droughts in a 1 week. Beyond 1 week, you see that start seeing the effect of drought. Like for example, agriculture. So the people start seeing the reduction in the groundwater level slowly, not in a very fast. So it's fast. So that's why there are some slow process, there are some fast process. So each have different type of forecasting. So that's why there is an extended range forecasting. Another is a long range forecasting. Long range means what is a mean monsoon rainfall for next 4 months. Like for example, monsoon season comes. What is a mean monsoon rainfall we can anticipate in this next 4 months? So that is most important for the government perspective, because policy decisions and all those things. That is most important because government asks us to what could be the weather, what could be the rainfall that we can get for next 4 months, monsoon months. So that is most important for it. So that type of policy decision making, which is very important for it. The long range forecasting is very important for those type of situations. Okay. Yeah. Next slide.
change only.
Range weather forecasting. So there is another center, IITM, many of you know probably, Indian Institute of Tropical Meteorology. So that will deal with the subseasonal to seasonal. Subseasonal is like I told you multi-week. We are also running multi-week because we are together working. So that basically sees that center will see on the climate scale and subseasonal scale. Okay. So there are various centers which are dealing with all those different phenomena. But all our centers we support to the IMD, because IMD is a front end to all our centers. So that will actually deal with the public. We don't directly deal with the public. Okay, so that IMD will, so all these models, whatever we are running, we share our forecast information to the IMD. So IMD will spread all these news to the various private and public, and even it goes to the public. So these are authenticated, whatever they are giving, that is authenticated one. So all this background we support them to show the forecast on a daily basis. Okay, so let me get what is NWP, because I was talking yesterday from today. So because those who don't know what is NWP, so NWP is a numerical weather prediction. So what is numerical weather prediction? So it uses a lot of mathematical models or equations that govern these winds and thermodynamics. So I will just go through the next slide. So it has several components. So yesterday I think you have already saw this. So we have an initial condition and data assimilation. So that is the first part. What is initial condition? We will receive all the observations and compare the initial conditions. And data assimilation. Yesterday I just discussed it briefly. Assimilation means what is data assimilation. So all these observations we receive and we assimilate equally along the earth grids. Okay, then the governing equations. The next part comes the governing equations. So because once the initial conditions are ready, so we supply that conditions to the model. So the model will prepare the next time step. So because for getting the next time step, we need the current time step. So that is most important. So then there are various numerical processes. I will go very briefly here. Next slide. So boundary conditions and physical cost. Yeah. Okay, no problem. So yeah, this is what first step is, like initial conditions. So you see the aircraft, MoES and ships data. We all receive lot of data. I mean AWS. You name it, we receive all the data at our center across the globe. Okay. So we have the GTS network. So through that network, all these data we will get from the across the globe. Now all these informations, what we will do, we will put a data assimilation module. So that will combine all these observations, whatever we receive. So what you have to see one thing. See, suppose I want to predict at Bhubaneswar and Cuttack. I don't have all the observations, right? We don't have many observations. Maybe I have one observation in Bhubaneswar, one observation in Cuttack, or somewhere else one observation. But how I can get the information in between? Because for preparing the initial conditions, I need each and every place observation. So we don't have observations at each and every location. So that's why what we will do, we will, within the process, we already run some model background previously. That model will run for current condition. Then we have an equal grid. Within that, we assimilate the observations. Okay? So at equal spaces. Because observations we don't get at each and every place across the globe. So that's why we run some model. Then we assimilate. Inside that, we assimilate. So whatever the errors that are coming from the previous forecast errors, that we adjust using these observations. Okay? Then we prepare. So that's where the observations are most important. And also previous model forecast we use. So that's where this, so what we call in our terminology is a first guess. This first guess means model will create a first guess across the globe. Then within the grid we assimilate. When we receive the observations, we assimilate within those grids. Okay, so that the errors will be reduced. So then we have a good, at least a reasonable, reliable initial condition at the current time. Then we give these conditions to the model. It will run for next 10 days or whatever the ranges I told, like 6 hours, 10 hours. Okay, it goes like that. Okay, so this is a process what I showed you just now. So if you see that bottom plot, so observations, model state. So observations we get and previous model state also we get. Within that we assimilate here and we issue a forecast. Okay, like that. But what that chart, the graph shows is, see, suppose let us say assume a practical example, like for example you start a car which starts with what, 0 km per hour, then it goes to 10, then it goes to 30, like that it will slow on increasing. So observations also, current temperature, only using one particular temperature, we may get lot of errors. Suppose if we get a window like plus or minus 3 hours, if I use all the information within the minus 3 hours or plus 3 hours, then I can know a reasonable estimate of the observation. Like what is your car speed, average speed, perfect observation. So because if you take it at one singular point, it always give a lot of errors. So that's why what we will do, today I want to start, so we go for 3 hours back observations, whatever we receive across the globe. After 3 hours, whatever the global observation we receive, all these observations we make an average initial condition at one particular point. For this what we will do, because if I want to start a model today, but I am taking 3 observations after, 3 observations backward. Now how I can get the information at this point? So there are some mathematical equations. Those who are on mathematics side, they know that they are called fast forward Newton-Raphson method and backward Newton-Raphson method. So we use those type of Newton-Raphson forward backward integration. So model will go, Newton-Raphson will integrate, will fast forward and will come backward. So using these observations, we move forward and backward, and we create a best initial condition at this stage. Rather than using single point, we take the time also. So this is the most complex process of data assimilation. Okay, those who are in this field, I mean, I don't want to go deep inside, but yeah, this is how we do. Rather than taking a single point, single time, instead we go Newton-Raphson, integrate taking the observations, we move forward, backward. Okay, within the 6 hours window, whatever we receive based on the Newton-Raphson methods, forward, backward integrations, we create a best state of the atmosphere on a current 0. Let us say whatever time we are interested. Okay, so what we will do, we actually forecast every day regularly at a regular time. 00 UTC we call. 00 UTC is a 5:30 hours locally. Okay, that is UTC, Indian Standard Time is a 5:30 hours after. Okay, if I say 00 UTC means it is 5:30 morning at our place. Okay, so that where we start our model and give the forecast for next 10 days. Yeah, go next. Yeah, so this is how overall what I told. So you have background information from the model, you receive the observations, yeah, you mix a grinder and you give a initial conditions. Yeah. Okay, so the next part comes is a governing equation. So what are the basic engine for this prediction of weather? So these are the basic governing equations. Momentum, thermodynamic. Yesterday I think Professor Mohan also mentioned. So what you see here, there are very few variables like V, dV by dt. What are this one? So V, temperature, density, and humidity. So there are only a few variables only we predict in our NWP system. But all the other fields, whatever the clouds, rainfall, all those things what you are getting is based on the post processing. So this is a major variables only we predict. These are called Navier-Stokes equation. This is a very simple form I mentioned here. So these are the major variables. Now you see the time. So what we do is a time step. Okay. So it's a time derivative. So you have an initial condition, then you can predict the next time step. So this is how we develop. I mean, these are the basic fundamental equations for any NWP system. Yeah, I don't want to go too much information, but what it will give. So it is so this is how basically what happened. It's a non-linear type of advection. See, suppose in atmosphere, dou U by dou T, what it means is minus U into dou U by dou X. What it implies actually. So the rate of change of wind is depending upon the gradient in X, and also it relates directly proportional to the wind velocity. It means that different components within the wind will move fast and slow. So some waves will move fast, some waves will move slow. Okay. So after some time what happens? The faster waves will move fastward, slow waves will be slow. So there the non-linearity will come. Okay. So that's why I don't want to go more details, but those who are interested, we can discuss later these things. Yeah. So yeah, you can just once go back. So the one of the important criteria I want to mention here that is, I don't know, see, this is delta T equal to. So this is a fundamental to any model. What is a model time step you are giving? So see, for example, I can predict next second also. I can predict next 2 seconds also within the using these equations. But I can't do that because there is a condition we follow that is called CFL criteria. But what it will give, any wave within the atmosphere should not skip. It should go each and every grid cell within the atmosphere. Suppose if I put at 2 seconds, that wave will move even faster than what we put the model time step. So it will not go into that time step. So we can't. So there that non-linear, that condition we have to satisfy. I don't know how much I gave you information, but anyway I will skip that part. Yeah, so yes, what is vertical boundary condition? The next step is vertical boundary condition. So see, in a global atmosphere, you don't have a boundaries, right? You don't give any boundary conditions. But suppose I want to run for a Bhubaneswar area, then I have to supply the boundary conditions. Because what is the wind at the boundaries after the Orissa region? So boundary condition is that any regional model, if you are running a regional model for some particular region, then you have to supply the boundary conditions. The lateral boundary condition is what is your orography, what is your mean sea level, what is all those things that comes in a lateral boundary condition. These are most important for any NWP system. Okay. Okay, yeah, you can. So once these models will start, so there are a lot of processes are happening within the atmosphere. So all these processes, see, model will not understand. What we tell, it will do the same way, right? What we have to tell the model, okay, now there is a humidity is this much, this is a temperature. Then you give a rainfall. That we have to tell the model. It will not predict its own. So all these equations, whatever in mind, we give in form of equations. Okay. I have this much temperature in this room. This much humidity is there. This much wind velocity is there. Now what is the temperature for next state? So we derive based on we assume all those equations. So that is what we call a parameterization. Okay. So we create. So model, as I told you previous slide, model will only give winds, temperature, density and humidity. It won't give any other things. Now it is our job to give the model, okay, this is a temperature, this is a humidity, this is a temperature. Now whether the next time step model will give rainfall or not. That we have to tell the model. That we will give in the form of equations. So that is called the parameterization. Okay, we give the model. So based on this information, whether there is any rainfall or there is any heat wave can happen or not. So that is called. So all these process, this is a complex process going on within the atmosphere. Like there is a microphysics. What is the radiation, sun radiation? So the radiation parameterization, microphysical parameterization, surface parameterization. So all these parameterization, if I say a word means, so we are giving the model what could happen under these conditions. So that is called the physical parameterization scheme. Okay. So overall, what I told here, I just put in a single slide. This is a basic slide for any NWP suit. So you have a observations within some window. Like I told in our center, we will take plus or minus 3 hours window, and then we have a first case background. Background means model will already issue the forecast at this current time, and here we have observations. We will assimilate here. So that's where these things, and then analysis, all the data assimilation, and we forecast the model. Once we have a forecast, we have a. Now the next job is to see whether model is good or not, and what type of products we can generate with those models. All those things we do next. Yeah, so these are the basic 3 analysis. Analysis is like creating observation, prediction, and post-processing. Yeah. Okay, what is our capability? I just showed here. Yesterday also I showed this picture. So what we are giving a 12. So you can actually use any of these data or data. Okay. So we are giving a 12-kilometer global resolution model, next 10-day forecast. Every day we run for this model, and it will issue globally next 10-day forecast at every 12 kilometer on the earth. Okay. Now you imagine how many computations that model has to do within that if it runs globally. Okay. So that regional model, which is a 4 kilometer, it is specific to our Indian subcontinent. So what we will do, because we don't require all the information across the globe for our Indian weather. So what we will do, we run separate model for Indian regional model at every 4 kilometers. So if you want to temperature, rainfall, at every 4 kilometers we have a data for next 72 hours. That is called regional model. Another thing, we run for a city scale modeling. City scale means we are now currently we are running for Delhi region specifically at a 330 meter resolution. Okay, at every 330 meter over the Delhi region we have a forecast data. So what this model will give a fog forecast, air quality, all those information it will provide over the Delhi region. So we can extend this to any other city if they want. Okay, so basically Delhi is most any small thing it will propagate like anything. So nationwide. So that's why Delhi they have put specific focus. For city scale modeling, we only run for 330 meter resolution for Delhi. Ensemble prediction system, as I told, see, you can't, even myself I'm telling, whatever it is, we decided these equations. Okay, so there is a fair chance that the model may fail. Always it will not give a good forecast. So because we can't control the weather. If I say that next 10 days what could happen, I am a god. So okay, at least we have to give an anticipate. Okay, this can happen. Okay, so that's what we will do. So we know our limitations, that we receive some uncertainty, and all the data whatever we are receiving across the globe. See, there is some remote person, let us say in Aravali or hills, whatever. There is some instrument. That person will go and observe and give us rainfall. I mean, how much you think that he will give proper? He may give just like that, whatever comes in his mind, 10 millimeter, 5 millimeter. That I don't know. Okay, so that is the situations we have. Sometimes what happens, instrument they put like it should have a vertical. What they will do, they will put in a slantwise. So that will give an error to us. Suppose we assume that model is installed at some ground, but what they do, they will install at some household in 10 meter 19 floor building. That we don't have information. So all those practical things you have to know that why the weather models are failing. Okay, so always don't think that why this always this won't give good forecast. So these are some of the practical problems we face, because you need to have a good initial conditions, good state of the atmosphere. I should know first what is happening at this time. But if these are the practical problems we are facing, how much you think that the model will give good forecast? So it won't give good forecast. There is some uncertainty. So that's why we know our limitations. What we will do, we will perturb our initial condition itself. Okay, that person may give actually 5 millimeter rainfall, but he gave 10 millimeter. So that we know. So that's why we gave from 5 to 15. Bad. We pet up our initial conditions, then we run the model. Again, like that we gave 44 times we run the model with different initial conditions. So how many more forecast I will get? 44 forecast I will get. Within the 44 forecast, how many of the forecast is giving more rainfall? So let us say out of 44 thing, I have 30 members are showing rainfall. It means that there is a great probability that okay, there is a rainfall. So because you don't understand, okay, I can give 100 millimeter or whatever, 50 millimeter. If I say that there is an extreme rainfall in your place, that is enough for you. Okay, I think we should be careful. So that's why we give a probabilistic way. So that is why this ensemble prediction system we also run. So we pet up our initial conditions and we run the model for 44 times, 44, 50 or whatever you decide. So basically we run for 44 current our capabilities. With our HPC we are running 44 times globally at 12 kilometer resolution. So at every 12 kilometer you have a 44 forecast. Within the 44 forecast you have 30 members are showing a rainfall means you have a good probability. Like 40 members out of 40 are showing, then there is a 100% probability that in this place rainfall can occur. Okay, that is what ensemble system. So again coupled system. So why this coupled system? So see, ocean plays an important role, but sometimes ocean is a very slow process. Okay, it has a heat. See, it has higher heat capacity than the land. Land heats very fast, but ocean heats very slow. Okay, so there is a difference between these two. So all the processes which are impacted by the oceans to the atmosphere are very slow. Okay, so that's why for long range forecasting, suppose I want to predict beyond 10 days, then the oceans play a major role. Okay, so that's why any subseasonal, next 40 days or season, if we want to predict, then we have to couple the ocean. We have to take the feedbacks from the ocean as well. Suppose for next 72 hours or 10 days, it may not be that much important. Ocean does not play any important role. Their atmospheric model is enough. Okay, that is one of basic assumption. So that's why all these coupled systems, coupled with ocean systems, that will be useful only for forecast beyond the 10 days. So yeah, I don't go much details, but there are various. See, we have to verify. I am working in the forecast verification team. There is a modeling team. There is a data assimilation team. So my job is once all these first model runs, all those assimilation forecast model, then the forecast comes to us. Then every month we verify the forecast. Okay. So the best way we verify in different ways. Okay. Different. I don't go all these details. It will take like 1 day to me. So there are various ways we will analyze our forecast. Yeah, next slide. Yeah, go to next slide.
Next slide.
Yes. Yeah, just go back. So one simple way how we verify I will show here. So what you see here is a cyclone here. Okay. So how do we verify? So that patch what you are seeing is from the observation. Okay. But the line what you are seeing is from the forecast. Okay. So now if you see the right hand side, the blue line is actual our forecast object. Object means it is the rainfall more than 100 millimeter, we put an object, or 20 millimeter, whatever you decide the threshold. So we create an object. So the red patch is observation rainfall. The blue line is a model forecast rainfall. Now you see what is the difference. You are choosing a lot of observation. There is a shift in the forecast. Suppose if this forecast comes to very close to the coast, what happens? We don't have a forecast, but there is a severe rainfall at the coast. So these are the situations. We have to tell the modeling people that this is a problem we are facing. Okay. So this is one type of verification. So what we do here, forecast verification is, so you see the objects right in the previous slide. So we give a centroid, we gave the orientation of the object, all those characteristics of that particular object we decide where the model is failing, or it is an orientation problem, or it is a centroid problem, where the model is failing. So this is one type of verification I'm talking about. Yeah, go ahead. Go ahead. So now let us assume, I'll give you a task actually. You see that graph, right? Image. So O means observation, F means forecast. So the object I showed you earlier plot, I gave in a different dimension. Now you tell me which model, like A, B, C, D, E, right? I gave A, B, C, D, E. Which one actually give a better forecast? A or B or C or D or E?
E, sir. E.
Okay, why E?
E.
Okay, why E?
Because most of the observations are
Belongs to
Okay,
forecast.
so you are telling this is most matching with the forecast. But imagine a cyclone which is came under the coast. Now you have an observed and forecast matched here, but all this whole area is a false alarm, right?
Yes.
Now suppose assume that government, for example, if I give the government this particular chart, okay, cyclone can hit this whole place, but actually what happened, observation is here. But all this area, whatever the area, government has to shift all these people from affected to the, so it is a lot of false alarm, right?
Then A,
Yeah, because why? Even though it is slightly shifted, because the area orientation is properly forecasted by the model. Okay, so that's why you need to understand. So there may be false alarms also. False means model will predict sometimes. That we have to be careful. Okay, so the A is good because observation and forecast characteristics of that particular rainfall object match very well.
B can also do.
Why B? B orientation is there, but
very distance.
so it means that you are predicting the forecast in
And
Orissa,
somewhere else.
but it happened in somewhere Cuttack or somewhere.
Yeah.
So that's where. Okay, yeah. Okay, so where the errors? Now you need to understand there are different type of errors. I don't go deep here as well. So there are two things. Major errors can happen. One is a systematic component. One is a random component. What is systematic? So sometimes what happens? Our models are predicting at a particular place, like Bhubaneswar, for example. It over predicts always. But it can't happen in this region. It means that systematically model is showing at this particular region some rainfall. So that is called systematic error. Model is systematically giving the rainfall or temperature at this place, but it is not happening here. So that is a systematic error. Random component is something like for example, any observational instrument which is not mounted properly, that is actually creating error inside the model. So it is most complex random component. We can't actually reduce this random component because systematic component we can actually correct that bias, but random component we can't correct. So that's why there are two things, systematic and random components within the forecast errors at least. Yeah. So now you tell me, so just go back. Okay, now, so what I gave you here, this is observation, okay? This is a 24-hour next day forecast. This is 2 days, 3 days after forecast. This is 5 days after forecast. 5 days after forecast. So what you observe here? So consistently what happened? As the forecast time is increasing, you are seeing the wind strength is very strong. Okay, it means that model is predicting lot of wind bias. As the forecast time is increasing, but the model is showing a lot of strength in the wind magnitude. It means model has some systematic bias because it is overestimating the winds. So this is called a systematic bias. Okay. Yeah, next. Okay, I just give a simple slide. This one, where the forecast can go bad. So there are two places where the forecast can go bad. Okay, one is the initial condition error, one is the model error. Okay, what initial condition? So as I told you, if you are this is the actual initial condition, but what we are giving because of these uncertainties in the model observations, we are giving initial condition here. Okay, that will create the forecast. So this is a forecast here. So model is here, but actual observation is here. So there is a lot of difference when you okay, it's touchable. Okay, then I can use it. So one forecast error comes because of the initial condition error. Because this is the actual observation, but you are giving here. Because that's why model is giving wrong error. The other error comes even though you are giving perfect initial conditions. Assume that you are giving perfect observation or observations, but because of the model physics, because I showed you some equations later. This is our assumption what we applied to the model. So that model physics also will give you the error. So there are two places where this model can fail. One is the initial condition and one is a model. Okay. Yeah. So how do we overcome these type of errors? One way, as I told you now, ensemble prediction system. So what we will do? So this is a single forecast. Okay. But what we will do? We will put up all these initial conditions to several initial conditions. We will put up these and again we run the model. So now what happens, instead of single forecast, I get a multiple forecast. So within the multiple forecast, suppose if 70% of all these lines are issuing a rainfall means, so there is a fair chance that okay, there can be a rain can happen at any place. So that's why I showed what all we receive. Like what you see here, there are 44 different type of forecast here I show. So our center will produce all these forecasts, and but we don't translate, we don't give this to public because public will not understand this. What we'll give? We'll give a probability. So out of these 44 members, how many members are showing based on the some probability we give? There is a 90% chance or there is a 70% chance. So if out of 44, 70% of members are showing the rainfall means we issue a 70% forecast. 70% probability that there is a rainfall. Yeah, next. Yeah, I just showed an example how we see. See, the novel thing is how we give a public in a proper way. Because if I tell this to any common people, they don't understand what is a 2 millimeter, what is a 3 millimeter or 3 millimeter, whether it can rain or not. Some people don't understand. At least some physics and math, those we know that okay, what is a magnitude means. But any common person they know. What we have to tell in a probability sense. Okay, there is a light rain, moderate rain, heavy rain. So this is where the novelty comes. You have to decide how you can translate your NWP models to a person who is a layman, and how you can give him the proper information. So translating this information to a proper understandable information is most crucial for any NWP system. So not only running model, it is also important you give the public in a proper way. Okay, best way how they can understand. So that's why we do a lot of these type of research that how best we can actually give the information. So here what we did, instead of single forecast, we actually divided that light rain, moderate rain and heavy rain. So at least 50-60% people understand, okay, light rain means here blue, okay, and moderate rain means some green, heavy rain means red. Okay, there is what is the chance here? 90% chance that this region can give a rainfall. So like, so how to translate those things? Okay, this is one way to reduce the uncertainty in the model forecast. Okay, then yeah, go ahead. So this is one way. Ensemble system is one way to give the probability to the public. The other way what we do in our center is we run a lot of statistical methods, but I don't go all these details. So you know already model has some systematic bias. Just in the previous slide I showed that there is a systematic bias. Model can give rainfall at single place very much, but instead it is not happening there. So we know that this model is giving lot of over forecasting of rainfall. Then what we do, we take the climatology of that particular location and we take the mean and we remove that bias, okay, using the statistical method. So we know that model is giving, so we can do that easily, systematic error, okay. The random component we can't do, but at least systematic thing is we can do. Suppose let us say our model is always giving in Orissa huge temperatures, like 30, 40, 50 degrees, always it is giving. But we know that we take the observations, but it is not happening that much temperature. Then we see all the historical observations at that particular place. What is the model is giving, what is the observation is happening. If you take 10 years of that particular location temperature information, then you know that this is a bias. Model is giving 5 degree more than the actual observation. That 5 degree we remove from the model and we issue the forecast. Okay, that systematic bias we remove from the forecast. There is a simple way I told you, but there are complex ways here we can do. There are several model outputs at quantization and all those Kalman filtering, all those things. Some people neural networks also. You know AML is coming, so AML also we are using to reduce the bias.
Here we have AML group sitting.
Yeah, that's the one. There are different ways. I will tell you in the end my class that what ways actually you can contribute to this particular, or you can use our data. You can give them public. I mean, this is the most important challenge because I came from a R&D background, but when I came to this center, so I understand that okay, not only you publish paper or do something which is of no use. We know it is for our use. We publish papers, but sometime I was thinking when I joined here 5 years back, my job is okay. I will have to publish like 10-15 papers in a year like that. But slowly I get to know that okay, this has to translate to the operations in the best way. So how I can give a public some information? Of course, do my papers this other way. We can do parallelly those things because we know how to do research. But the best way, use our forecast and give the public. So we have some internal satisfaction that okay, I did something to the public. That okay, this best way I can do. Okay, what, suppose let us say in Chennai, we started this, there is a flood warning, you know, Chennai and Mumbai, this lot of flood things are happening. So we try to do this type of statistical post-processing, and we somehow made that biases to reduce. At least this fair amount of forecast we are issuing for them to issue the forecast to the people. That is such type of things. So research to operations is most important now. R2O we call, that is most important. Okay, but anybody can use. So what I am telling is you have come from different fields, but you have a scope to work with our data and do your job. Do your research and give a public some information. You give us some whatever the code or application you develop, you give us, we use our own in our sector. So that way these projects will work. So you write some projects, use our data, write some project on your own domain and give us that application later. Ministry is funding, there are a lot of scopes, MoES is funding and DST is funding, ANRF now came, ANRF is funding, all those funding agencies we have. Only the thing is you have to sit, think how I can do that work. Think and write. That is only you have to spend time. If you do that, you have an ample opportunity because we are giving freely the data. Now government mandate is you give the data anybody wants. Suppose you send us some email, we have to send you the data. Otherwise that is what we got the mandate. So it is a public data we are using. It's a taxpayers' money we are running the model. So we have to give them to the taxpayers. That is what this mandate gave. So anybody who wants the data, our data, they can use. Okay, yeah, so next. 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 You go to the next page. Yeah, so I'll just rewind up some of the things. Okay, so yesterday I showed you this picture. So what we are doing is we are thinking that oceans also plays an important role. Over the past 30 years, for any forecast we are issuing in the medium range, like 10-day forecast, we are not involved the ocean in our forecast. Now, from the last year, we involve the ocean feedback. We are taking the ocean feedback to the atmosphere and then we are issuing the forecast. So that type of some major achievement, this is why we thought is because oceans can also play important role within the 10 days. So that's why we assumed that and we started this by just giving good results as well. The other thing is we are running a global 6 kilometer model as well. Because now the computation power has increased, now demand is also increasing. People are coming that what is temperature or rainfall in my rooftop. That is what the people are wanting. See, suppose government is like the solar power project came this PM mode. So that after that people want the temperature forecast as well at their rooftops. So what is your temperature? At their based on that you know what is the power you can get. So you have a temperature, wind, and all those information. You can your own model. You can create your own model. Now ChatGPT and other things came. So you give the idea to them and it will create at least the script and it will run that model. You give temperature or solar radiation. What is the forecast, solar forecast I can get next 10 days? That we can get. Based on that, what is the solar output I can get for my home? That also you can do. So that is how the situation came. So that's why we are going on increasing our resolution. Now currently we are capable of running at 6 kilometer globally. Okay, that's what you are seeing here in the middle panel. So you see the convective plumes, very small plumes. These type of very small plumes we are getting. So those are resolved by the model itself. Okay. Because model itself is generating those particular plumes, convective clouds. Okay. Earlier what we are doing, mathematical models are there. Those are creating the convection clouds. But if you go higher and higher resolutions, model has its own capability. Okay. You don't require any model. Model will generate its own convection, its own clouds, its own rainfall. So that's why as you go higher and higher resolutions, the manual intervention of these mathematical models, parameterization, what I told earlier, it is not required. Model will create its own rainfall, its own clouds within that 6 kilometers. Okay. But if you go for larger regions, then the schemes are important. If you go higher resolutions, model will generate its own convection. Okay, the other thing is AML. So those many of you interested. So what we are doing here, we are experimentally running currently 3 different types of global models. Okay, we have a capability to run all these models globally. So that we are running now. We are testing. This is actually very initial phase now. We are just analyzing how this is better than these physical models. Okay, how the data science is most. I mean, those who are in the data science, they can efficient use. This is a time. I think next 10 years, this will boom very much in every field Okay, so at least next 5 years I can say. Okay, next slide. Right, next slide. Okay, so now we have a physics-based models, what I discussed earlier. Now we have a traditional physics-based models. Now why we need a AML model? Because AML doesn't have any physics inside, but what happens? It will learn from the data inside. Okay, the complex patterns within the data it will analyze and it will give the next forecast. Okay, so that's why you need a 30-40 years of past historical data. Within that, model will assume different neural networks, like your brain. So if I see many people, I can assess at least if I talk 10 people, I know what their mindset will be. So your mind is capable of distinguishing 10 people at a time. Same thing, the model, it's a brain, neurons. So that word came from that. I think many of you know already. So the neurons inside your brain is same as a neural network inside the AML models. So the different learning patterns we give to the AML model and we give the data. It will understand what can happen. It will give the forecast. Okay, I don't go more details actually due to time. Yeah, that's right. Yeah, go to next slide. Yeah, I just go back one slide. So here, why we need to run this? First of all, we have a strong infrastructure because these models are very complex, so we need to have a high computational power. Then the other thing we need is a data because all these things are training with the data, so we need a data. Okay, so the data we have already 40 years of climatology. Suppose you want to use the data, that data is available freely in our website. Okay, you can download the data. So then we have a national responsibility as well because we have to go with the wind because all the operational center across the globe, Europe or US, they are also running and we have to be in cope with them as well. So that's why we also have some national responsibility. So that also we are using this particular AML models for our weather forecasting. Yeah, just go next. Yeah, I don't go inside, but what it will, there are different operational models globally, weather forecast models, AML models. So it is called Pango Weather, which is developed by I think Pango is China. GraphCast is a DeepMind, Google DeepMind, I think. And then ForecastNet is NVIDIA, and Aurora is another AML model, which is done by Microsoft. So there are different global private partners played to develop these particular models. Okay, so of course they take our weather forecast data as well. And each model has its own different type of methodology. See, the Pango weather, it will take a latitude is the space and height dimension, and it will ingest into its AML model. But unlike ForecastNet, what it will give, it will assume that in sort of a sine and cosine waves. Okay, based on that it will train. The GraphCast is like each it's a nodes. We call nodes. Nodes means each and every location is a node. How the information is transferred from this node to that node to other node. So that way these models are trained. Okay, each has a different type of training methods. Okay, yeah. So I just showed you for example. We just go back. So one example I gave you to feel how these AML models will run. So currently we are running in a real-time basis, but we are not issuing any publicly. We are not issuing forecast based on this, but we are running experimentally. We are just checking how best these models are compared to our actual numerical weather prediction models. So these three models I showed here. Now basically what you see here, I think reasonably on the seasonal scale, they're actually giving very nice. I mean nice the flow across the India during the southwest monsoon period. So on a seasonal scale, these are doing pretty good job in my sense. But I don't know how much local scale this will give best compared to our NLP models. But you see here, during the monsoon we have received a forecast southwesterly flow. This flow is very nicely picked up by the model, all those models. Next. Yeah, one advantage of using HPC is this. So I want to forecast for next 10 days globally. So if I use CPUs, our CPUs, it takes around 47 minutes for us to compute for forecasting. But if I use GPUs, NVIDIA GPUs, we have used like one GPU at present. With one GPU, we just finished this particular job in 4 minutes. So that is how the capability of using the GPUs. So for example, Pango weather, it actually takes like 1.5 hours to compute for next 10-day forecast globally. But it just takes 11 minutes. usage of CPUs and GPUs. So the model we are running 3 different models. It takes 47 minutes to run a global weather prediction model in AML model. But if I use GPU, one GPU just took 4.2 minutes. So I mean for any renewable energy sector or any sector, people want fast weather prediction data. So it just took us just 4 minutes to compute across the globe next 10 days. Okay. So same way GraphCast. So GraphCast model with CPU, if I use, it takes just 47 minutes. But if I use GPUs, it just use 4 minutes. 4 minutes to compute all this process. Okay. Just next. Next slide. Yeah. So just to give a feel that how these AML models are better compared to the NWP. So what you see here, the black line is an actual observation, and all these magenta and pink lines are from the AML models. So I mean, all these models, even though they are trained with the data itself, but they are giving a very good forecast compared to the NWP system. The red line is an NWP model, physical based model, but all these other lines are different AML models. So I mean, this is very nicely given. I don't, because this is very, terminology is different, so I am not telling terminology, but you assume that these lines, this is observation and all these things are different models. So, but AML models. So all these AML models are giving very forecast, decent job. They are doing very decent job, but we are still analyzing this data, and maybe sometime later we issue the forecast using our AML models in conjunction with our physical models. Okay, so in our center, what we are actually doing? So we are doing some sort of a novel things. So using, always depending on some other data is always difficult, because we are using currently European Center for European Center data, but you don't know when they stop. Like for example, NOAA satellite recently they stopped after this Trump effect came, they stopped the NOAA observations. Suddenly our data reception stops, and that affects our forecast. So that's why independently we should be always independent. That okay, like Atmanirbhar Bharat, what Modi is telling, something like independent. So that's why what we are doing, we are using our own initial conditions to run these models, so that we should not depend on any other European Center or US Center data. So that's why here we are showing, we started this very recently. What we are doing, as I told you, the initial conditions are most important to run any model, forecast model. So we are using our own global model data, initial condition to run the forecast. So that we supply to the AML model. Okay, now we should not depend on any other data. We can develop our own forecast independent of other countries' data. So that's why we started here. This is the first example. I think we successfully done this. And so this is a European Center data, and this is our own initial condition data. I mean, you see recently it is our model, and their model is doing a very good job on a global scale. Next slide. Okay, so I think yesterday I also in my short talk I showed you this. So a lot of satellite data we are ingesting, ISRO satellite data in our center. But the thing is, whatever the AML models we are using in our center, it is trained by some other data set. Okay, it is a European data set or US data set. Now our next job is to use our own data to train the model. That's where actually the students, see those who doesn't understand the methodology or anything, if you have a data science knowledge, you have a data, you develop your own model and you train the model. We supply the data, you develop your own model, AML model, and give the forecast. See, it is a time series forecasting. So anybody knows, mathematical people know time series forecasting. It doesn't require any mathematical or any specific domain person, like we are from the meteorology background. You don't have to be in a meteorology background for an AML model. You need to have some knowledge about the mathematics and data science. That is enough for this type. We supply the data, you develop your own model, and you create the forecast. Okay, what would be the next 10-day forecast or whatever. So, but the idea here is we have to use our own data for training the AML model. That's what we have not done so far. Okay, we are using the already existed pre-trained model. We are supplying our initial conditions. We are issuing the forecast. But our next job is to train with our own data. Okay, so because we are receiving a lot of Indian domain data, so it is always good to train with our data and issue the forecast. That is always good. That's where we are still lagging. Next. Okay, so this is just the final goal I will tell. So development of new AML models. So that is what we are looking for many students as well. I mean, those who are working in this computer science and AML data science people, we are looking for them. For any intern project also, we have an opportunity. We will give the accommodation free for all the students. Like 10 students we select twice a year. So all those students we give the accommodation free. They have only for 6 months also. You can use our own HPC infrastructure and you can develop your own model. That type of facility we have. Okay. That is for the students, those who are here. Okay, so yeah. So all these two models which requires enormous amount of power. As I told you, needs a GPUs, it needs CPU, enormous huge number of CPUs and GPUs. So yeah, do this right. Yeah, so this is our actual Arnica supercomputer overview. Actually my HPC team doesn't allow me to share the slides, so I just put in a one slide all this information just to show you what is our structure. So we have a total, those who are from the computer background, they know this. We have a total 2,150 nodes. It is top 200. Our system is in top 200 across the globe. This HPC. So then we have each node which have a 96 CPUs. Okay. So it has a 3256 GB RAM. I don't go details. Actually, there are different type of architecture we follow. But GPU nodes, NVIDIA GPU nodes we have. It is like 80 nodes we have. Each node has again 96 core processors. Okay. So it is a very decent infrastructure we have for in terms of GPU as well to run our any complex models as well. Okay.
Any questions?
Yes, sir, you talked about the ensemble model, right? And you talked about running the model for 44 times and getting the ensembling out of it. Is it only confined to that tagging tunes, or you have different models that runs number of times and you are getting output and ensembling?
No, same model.
Same model.
Yeah. Let us say you receive an observation. That observation, we know that observation has uncertainty. It may be correct or wrong. We don't know. See, we are sitting in Delhi. Suppose if I receive some observation from Bhubaneswar, this person, whether he has given me proper data or not, that we are not sure. So we run from this observation next 10-day forecast. We have some uncertainty that we don't know what is the observational uncertainty. That's why what we will do, we assume that it has some uncertainty. We will put up this observation to 44 times. Okay, same observation. Model is same here.
Model is same.
Model is same. Observation is different.
Normally in ensemble model in AI background, we do actually multiple models we go for.
Yeah, there is another ensemble. So ensemble is another scope is you use different models with different physics.
Then measure of coding will be
Yeah,
taken.
that is you put a common. But here it is not like that.
That is not the case.
It is an actual observation we put up. Inside that there is some complex schemes also we put up, like physics schemes inside. But I'm not going to. But here assume that we put up model is same. We put up here.
And so one more question, because you have said like it's very little interventions of AML so far the prediction is concerned, practically coming out from the IMD is not there. I think it's a very initial phase you are talking
Yeah. Nowadays, so far only all the forecast issuing based on the physical model.
But other countries like US and they are using deep minds, that is GraphCast.
They are using nobody is giving any forecast. You see in Europe or any other sites, they put bracket experimental. They will not give. Physical models are still they are running. They are depending on that. But they write experimental because they want to show how slowly they will see how best this is.
In the recent article they have mentioned that GraphCast is doing excellently well.
Excellent job for research paper. See, you have to come with an operational point of view.
No.
I can do hundreds of research, but if I go back my first paper, I'll see there is some problem is there. you write your own paper, right? I mean, you assume because I wrote my paper in 2005. Now I know that I did some problem there, but it published. So it is a research. But when it comes to the operational standards, we have to be very clear. There are some SOPs, standard operation procedures we follow that it should properly give. It should not it's stable, do the decent job, decent predictions. Okay, like that. So all those things.
slide was showing that it is very promising.
Yeah, promising. Yeah. That is actually one variable. That variable we don't issue. But see, people are looking for rainfall, temperature, and all those things. So how best your rainfall? We can translate that variable into a rainfall. Then you check how it is best. Yeah. That it is not the rainfall. It is a total column water vapor. But how I translate into a rainfall? Then see the difference. Then we should be confident. That is only one single case study. I just want to showcase here that we are capable to run those things. Yeah, we are running actually 2 monsoon seasons we have already run. We are now analyzing that.
Thank you.
Okay, I have a question. Because this 3 days workshop we are conducting for capacity building, but I don't know how get like yours, the big super company business. We have still access to iRavel. See how we can move forward. The team, how they can move forward to contribute. As you know, not in writing research papers, projects, or doing something real time.
So, madam, one thing is
For
we have this
localization.
National Supercomputing Facility. Government of India has set up several places. So, if suppose your institution doesn't have any supercomputer, you can write them
No,
an
we
email.
have access to
Access to
iRavel.
that iRavel. So you can
We have Shavak, then now we have access to iRavel.
access to iRavel.
Huh.
That is one thing.
Huh.
But if you want to use our own system, so for research purpose we allow, as I told you, so people can come there, you write a proposal, no need to write a proposal as well. We have in our website, if you go, there is a always scrolling is there, that intern, dissertation, 1 year project we have already. So those people we already give the infrastructure, all the access to HPC and all those things. That we, but only 10-15 people we take because we are giving a free accommodation to them in Delhi. So
But any virtual things will be okay, you can give us access to your, that is not possible.
because the problem is this is an operational center.
Okay.
Nowadays people are very smart. See, I work. I'll tell you an example, very funny example. I worked in University of Tokyo as a postdoc. So what they did, some student, one of our friend, he was very angry with his boss. So when we go to that center, so we have a common Wi-Fi. Both professors and student has an access. What this computer fellow did, because he has a hack person, he know how to use the hacking and other thing. So he hacked his boss computer and he deleted everything using his Wi-Fi. so there are these are, now if all over India, if you give access to that system, already we suffered. As I told you just now, last 2 months back we have this issue. Our computer was hacked. Yeah, I don't know how they hacked. Somehow they hacked our system, and luckily, what they didn't use our data. They didn't delete any of our data, but they have used their Bitcoin programs. They run in our system. Okay, they earn a lot of millions of dollars because why we don't know 2 months they are properly running. We don't know that they are running. One day we checked our systems are very slow. Our operations jobs are becoming very slow. Even though we have availability of nodes, the jobs are very slow. Then someone got this why this is very much slow. Then this problem has faced somebody has hacked into the system and they use the Bitcoins program they run and they earn a lot of money with this their program they install. So there are crazy things are happening. so
No, once we have MOU, so what benefit we can
Benefit,
get? Because see,
MOU.
all that time we cannot go to Delhi to your center. Yes, yearly once our team
No,
can
ma'am,
go.
if you want to do some PhD students or something, they can go and
Okay,
develop.
let's answer. So
what I'm telling, see, there is a 1 year project is there, intern is there, 6 months intern is there. Okay, suppose you are sending a student to us through PhD also they can come. That is one way what we told. The other way is if you have an MOU, we can give our data on a real time basis as well, and we can give all the historical forecast data as well to you. Now you develop some application, you have some contact person. Mentoring, that's what I mean. One point of contact person will be there.
Oh,
So
that's
you
it.
develop application,
Yeah.
and you are benefited actually. We will give your name in our center that okay, this application was developed by this Trident Academy or whatever. Then we give to the IMD. IMD is basically operational. So what this application, whatever you are developing, ultimately it goes to the IMD, it goes to the public.
That's
Yeah. Suppose you are running like flood warning system. So people are interested in some flood model they want to
a
develop.
lot of
Yeah.
AIML works need to be
Need to be
done.
done using our data. See, you have an ensemble data. Now you run that model and you run the flood model with 44 times and issue the flood inundation in the Bhubaneswar. You develop some particular application for this particular city. Let's say Bhubaneswar. You want to develop, let us say thunderstorms are more important here. You develop the thunderstorm prediction system using AML based on all our forecast that we will give anyway if you have a mail. And you develop and you give us that application. That will be big.
And ma'am is also there, she can help us.
Right.
Sir, we can, I think, later we
Okay,
will
we
stop.
won't discuss.
We are
What do you think
taking
last time?
Okay, again a very big round of applause for